Takes a minute or two to populate the participants, but let that take place first, Garrett, and then good morning, everyone. My name is Daniel Hargreaves with CSINext, Electronics Chair and Chapter Treasurer, and welcome to our December Procrastinator Series, Part 2. And this morning, or this afternoon, it's getting later in the day for everyone. We have Garrett with Sika, and we'll be doing simplifying air and water resistive barriers. At the end of the presentation, there will be a survey. It should pop up in your browser with the option to move to the CSINext site to fill that out. If you don't receive that at the end of the presentation, you should get a follow-up email tomorrow. We'll collect that information and pass it off to Garrett so he can register this presentation, and it is an HSW credit. We'll get it registered with the AIA and certificates to those who need it. With that, Garrett, I will hand it off to you.
Outstanding. Thank you very, very much. Happy to be here. Happy Friday, everyone. Hope everyone is enjoying the preparation for getting to the Christmas holidays and in the Christmas holiday spirit. This is an honor to be presenting today, but it seems like this has been kind of one of those weeks. Tuesday, Wednesday, I've had full days of video conference setting in front of a computer as our national sales meetings and year-end meetings and business plan reviews. So it's that kind of theme week, setting in front of a computer and being on camera and being able to express information, wants, needs, and solutions. So thanks. I thought I'd share this kind of interesting background because I'm sitting in Chicago in the frozen tundra this week. And I would love to be anywhere else, specifically more warm than in the cold negative temperatures, as they say. So pleasure to be here. We're going to talk about some air and water barrier systems. I'll get some information going, but I did want to give you a little background without going through a full profile of myself. As you can see on my opening screen here, the description of the course, my email and phone numbers. I have gone through that transition of the gauntlet, I call it, of mergers and acquisitions in the last 7 years to where it was BASF, then a carve out from BASF from Master Builder Solutions. Master Builder Solutions then was acquired by a private equity firm, which was MBCC Group. And the brands that are affiliated with Master Builders or then everything encompassing were just purchased last year by Sika. So my email has changed 4 times in the last 5 years. And so that's that front screen there. If you had an old email that was BASF or Master Builder Solutions or MBCC Group, now it's officially Hovest Garrett at us.sika.com. So I'm going to take my camera off just for saving bandwidth, but at the same time, I got a face for radio, and I don't like to look at myself look funny on a beach with a jacket on and a sweatshirt. So hopefully that's okay for everyone. And hopefully everybody is doing great. That's it. All right, here we go. I'm going to give you a little bit of some information on some of the acquisitions that have taken place, a little background on in combination to prep up to the course here, a little bit of background on the acquisitions. Here at the bottom, you can see is that's the latest and greatest. Maybe familiar with some of those legacy systems with the Sika acquisitions over the years, and everything that goes in between. So you can see from the different divisions within our group of Sika, I kind of focus on the building envelope, below grade waterproofing, air barriers. So try to consider myself a little bit of a guru versus specialist in that building envelope arena. So here's some news articles that just placed with another acquisition from that a couple years ago. So it's been a fun roller coaster in that acquisition merger world. I'm happy to be part of this organization. So this is an AIACU Health, Safety, Welfare, HSW accredited presentation. Okay, the information that I'm going to be sharing. Hopefully there's nothing in there that's too brand specific, if at all brand specific. But if there is, please report me, and then I'll be living in a van down by the river, okay? Little course description here. I won't really read that. It's a paragraph of just sheer fun and exciting. But we're going to talk about some examples when we get started on field conditions. I'd like to give a little bit of a prep of what we see physically in the field that then encompasses the detailed information of why we want to get more involved in the understanding of how moisture moves in the air, different types of air and water barrier systems. But seeing those conditions out there in the field is very important to see what I talk about. You can see that physically in some of these pictures. So the conclusion is so you'll understand more about the material science that goes into the air barrier, water barrier systems, and the efficiencies around that from an energy and a sustainability side. Kind of be able to distinguish those different types of barrier systems. Okay, codes that kind of are relevant, sometimes confusing, sometimes, oh my, what are we still doing in back in the 80s kind of environment, and then describe those 5 requirements that are really important in the need for air and water resistant barrier systems to make the integrity of that building and last longer. Why is it important? Well, the materials that we use today, obviously for sustainability, is huge. We want to kind of minimize our carbon footprint. One, obviously, water is damaged, so that basically causes, maybe potentially structure failures, and we don't want to live in that what-if syndrome. Okay, but the biggest and most important reason when we talking about this category of air and water barriers, well, the largest reason is the surrounding the fact of litigation. It is the largest, most impacting litigated aspects of construction today in North America. I'll put it that way. Nobody wants to be sitting in the environment of either a deposition or on stand to ask that, oh, what if, or what did we cover, what didn't we not cover, and those checks and balances and means methods of what we did and how we did it and the impact thereof. So that's pretty much definitely encompassing part of that is the topic of the day is all those construction defects add cost and complexity to the construction projects if there is potentially a failure or if there's a potential issue with not addressing that from what I consider the get up personnel and in the pre-con meeting and the aspects of talking to the contractors, make sure they're doing it right. Because that's usually the biggest impact is that all the materials that we work today in this category all perform very well if it's done right. And this little quote here is approximately 10 to 30% of additional costs. Literally, when you look at the cost of a structure, we'll just use a flat number here around $1 million. Just use that flat. There's a survey that's done with Oak Ridge Laboratories. I know there's some consultants that were involved with this type of survey, but they estimated that the additional cost related to callbacks and rework were on top of that estimated $1 million. So you look at that 10 to 30% additional cost factor. If we do it right the first time, shouldn't have to worry about it, correct? So here's some those field pictures I was referencing that a little bit ago on what we see in the actual out there in the field. This is an example of utilizing a liquid flashing or a window buck framing system, or that sill of the window is basically a 2x of a wood material. And then inside of that opening, they're flashing around the jambs in the head with that similar type of material. And that's referred to as like a liquid flashing. And that could be a composition makeup of several different types of materials in the industry, whether it be an STPE, sometimes a PU, or even a silicone. But what is key is, I don't know if you can see my mouse. I believe you can. But up here in the punched opening of that metal stud is basically a opening for any potential conduit or electrical or anything from that metal stud framing. And as they flash in this inner, what's important about this is determining where the window is going to be within that opening. How far is it going to be outside or protruding to the exterior? and where the termination of that window is to the interior. If you have any potential leak in here to where it's not properly flashed and the window's terminated inside this opening of that punch out, guess what? That water directly has no way to stop from an interior perimeter seal if they're using a sealant or a foam spray and that interior to seal that window. Window's going to get into that area, or excuse me, water is going to get into that area. So then you talk about thermal bridging. That's a whole other factor in itself. We talk about dew point management, but I just want to point that out. Something I look for. We talk about the different types of air and water barrier treatment systems. Another is basically a reinforcement. The other is a liquid flashing. It's an inlay type of fabric to reinforce that seam with an air barrier material. And then there's self-adhered flashing or peel and sticks or other options as well as the types of seam treatment we see in the field. Here's some detailing of penetrations of interfaces that I see out there in the field, whether it be a CMU wall backup with a large pellet penetration, or how they actually will detail around that. Here's a perfect example. It was before, semi-after. We'll use a liquid flashing seal around that large penetration. Here, you come in as your MEPs. We'll see that a lot is your MEPs will come in even after an air barrier applicator has left the job. We'll have someone put a hole in there. Well, who's responsible for that? Who's going to detail it? Who's going to make sure that that penetration is being effectively sealed? Because that is an air and water intrusion point where it will just cause moisture in your building. Another areas here, again, conduit. This is basically air barriers applied, CMU. You got penetrations already. How do you treat around brick ties or embedded brick ties? A lot of times when we see Air Barrier Association, America, or other consultant testings on what kind of air leakage you're going to find in a wall, it's exactly what they'll do. They'll look for that, the weakest point or the path of most or least resistance, of where your air leakage is going to be. They'll put a cone test around those brick ties that are embedded, find a weak point, and see what kind of air leakage you're having. That's basically going to equal to a moisture factor. Fasteners that go into exterior gypsum as an example. There's a requirement through the exterior gypsum, say that's how many fasteners can be in that material. In that fiberglass reinforcing exterior gypsum grade material, if you overseat that fastener, is it giving you enough integrity structurally to hold the material on the wall and then be properly sealed for an air and water barrier system? There's a lot going on here with these pictures, by the way, okay? On the left here, you've got potentially 4 different types of materials and an interface at the base of the wall of a through wall flashing. You got a termination bar with a sealant. You got a peel and stick that's not effectively coated because it's got a polyester fabric reinforcement. You got a mortar net material in there that effectively isn't going to be turned in, and they're basically buttoning this up with brick, as you can see. So penetrations, fasteners that are going through the material, thermal bridging capabilities. Well, one is most hilarious here, and I say hilarious loosely, is in this corner, if you can see this is actually a 3-inch fastener that's in that head to jam interface. And there is these are basically Tapcon fasteners are going to go, they're not smooth, they're protruding. And these are, who owns that again as a scope of work? And is it causing the contractor that had put a bid in to do this work more time and material and labor? And if that's not accounted for, that means we're basically going to be value engineering the wrong way. Okay, it's going to sacrifice quality. Here's a little bit of an example of a mock-up. Excuse me, going a little dry here. Got to take a quick drink. Any questions while I take a little sip here? All right, golden silence. I like it. Here's an example of a little mock-up that I did with IMI. Basically, in those questions of what we see in the field, what is effective? What is a good application, or what is actually an acceptable substrate kind of details, a mock-up? We do these kind of things to basically make sure that we can see, hey, this is how we want to see that before the applicator contractor gets to put material on the wall. Here's an example of hey, what do they do or how do they do it, is spraying material on the wall. Hopefully, is this video working okay? I hope you can see it. Looks like it's working on my screen.
It's working on my end too. Thanks.
Awesome. That's a quick illustration of an applicator spring referred to as a prep to put the air barrier as a block fill material. I think everybody will know or realize that CMU or concrete masonry units or block are very porous, even in the grades of knowing that your material is a high or low or medium grade type of CMU, and that's how they're categorized in the field and the industry. Even when you believe you have a high grade CMU, there is still a lot of porosity. So this is to stop that ability for the air barrier material to soak in. You're basically taking a hole when you look at a microscopic blow up of a CMU. You're basically looking at that hole of porosity being about a quarter size, and you want to drop it down to the size of basically like a thimble or, a smaller diameter. You're minimizing the ability of absorption. What that means is you're losing the effectiveness thickness that the mills of the air barrier needs to be a true air and water barrier system. So that's basically a block fill, spraying it on, and that's it. So I can get this to advance. There we go. Here's just a close pickup. He was using the extended one. This is a short nozzle for your spray tips. And then here's a different type of application, as you can see, as a contractor. They're basically hand rolling this, depending on where your scope of work is and an area, whether it be union or non-union. That's really what dictates a lot of times is your efficiency or a speed or ability to put an air barrier type of system on the wall, whether it be sprayed, whether it be pressure rolled, or whether it be hand rolled. Sometimes in certain municipality areas or big city areas, you can't spray, or you want to minimize the ability for overspray or concern of having that spray paint a building or a car or an adjacent structure, and that's always an issue to look out for. Some challenges in our categories in air and water barrier systems. Mother Nature. Okay, there's an ability for materials to go down to 0 degrees, even less. That's not nearly as a concern from a standpoint of the contractors or trades, but it is what is an acceptable substrate. Our materials in this industry of a fluid applied air barrier specific system, some are acrylic, some are modified acrylic, some are polyurethanes or silicones, or a reinforced type of rubber, and some are water based. Even some of the materials that are referred to as a higher performance in that STPE or even silicone can get down below freezing temperatures. And that's great. Okay. There's several techniques to be able to keep the material warm, keep it from freezing, but you've got to get it from the bucket or the barrel to the wall. And whether you're using a type of piece of equipment and that material staying warm, but as it gets through a 50-foot hose or longer, it's traveling across the ground, it still has the ability, even though it's rated to be below freezing, to gum up or have problems to be able to spray or roll on the wall. So hand rolling, you see much more prevalent in some colder temperatures because the equipment is not suited for. Or what is an acceptable substrate? Your materials can go down to 0 degrees or below freezing, but is there frost or dissimilar material? Is there a ability for moisture to be on that wall? Every liquid applied material in this category needs to have a sound substrate for adhesion, proper adhesion to that wall or that substrate. And if there's dissimilar material, dirt, debris, obviously we live in the world of construction because it's always going to be dirty on a job site. But if there's frost or a dissimilar material on that wall, most air barrier materials won't want to adhere to it, have a good adhesion. So, here's a good mug shot of me using a pressure roller system. You can hear the pump. It's going over OSB. And then here's one actually going over an exterior job. So this is just a wall mock-up I did, the contractor site, showing that the ability for pressure rolling. We're using the pump and the materials fed directly through that perforated roller, and it goes right to the material. So you're not spraying, you're rolling. So, all right, fun stuff. Material science. What is material science? Well, it's the interdisciplinary field dedicated to the discovery of new materials with an emphasis on solids. Well, why is that important or want to know? This composition of materials that our industry make up is there's a plethora of different technologies out there. Okay, material science plays an important role because solids are what keeps the material having the integrity to stay on the wall. So in these different categories, you have mechanical fasten systems is materials that are basically using a fastener to stay on the wall. You've got your self-adhered membrane type of materials, or a sheet good, as we see, as a peel and stick is another another name for them, which basically requires a primer to go to your substrate so it can have good adhesion between the substrate and that material, or a fluid applied, or FA. Okay, and that's basically just your liquids in that standpoint of a bucket or barrel that's rolled or sprayed on, as I kind of mentioned before. So why is that important from a solid standpoint? Why is it important from a material science? Well, in that composition of materials out there in the industry, how this adapted from being a category in importance. We're used to having felt paper as an example back in the day, in the 1970s, 60s even, and going up to around 2000. You had materials that were basically just 15-pound or 30-pound felt. And those were a bitumen or asphaltic type impregnated type of material that had to be fastened on. Well, they decided that in around 2000, let's take materials that were truly below grade waterproofing, your thick bitumen and asphaltic based types of materials, 80 to 120 mils, let's bring them up on the wall, okay? And those were basically not a high solids content material, they're highly solvent materials. And those basically, you're basically using that solid material as a carrying agent. You get from the bucket to the wall, that solvent, high solvents in there, which was low solids, would evaporate through the carrying agents that are basically getting to the wall, from the bucket to the wall to stick. Then you put another coat on to have that material basically get to its performance thickness. Technologies have changed over the years, okay? So what we've used to do, what we've used to have, has changed drastically in the last 10 years. So you go, as an example here, from your old console TV, of your old Sylvania, to our, gosh, we can see a TV today that's 10 times larger for a quarter of the cost. Okay, you look at what technology has advanced from a material science, even from the tools that we use every day, as an example. So there has been a paradigm shift in the industry of seeing that your high build, really thick material systems, which would have that need for performance because it's solid space, going to your lower build or medium build systems. You're getting a higher performance for less thickness type of scenario. So that really plays into what we see every day, which is a curse word. Oh, sorry to bring this up, but it's value engineering. Well, why are we paying 2 to 3 times more for something that's going to perform equal to, if not better, even though it's got a thickness that's a lot less? So it's kind of the equivalent of using the analogy: you go into your favorite steak restaurant and you order a nice 20-ounce T-bone, and it's 20-ounce T-bone. When they put it on the fryer or the grill, when you get it, it's down to 4 ounces because you're losing the performance of those solvents versus solids content. Even though you're paying $25 an ounce maybe for that T-bone, it's a change on what you're getting to put in your value engineering stomach. So hopefully that wasn't a bad analogy. I can't see anybody's facial expression or a roar of laughter in the background. So, all righty, I'm going to switch over here to what are those types of systems themselves. First and foremost, you can define this in different ways. First and foremost is bulk water. In everything from a design standpoint, if we have the most common aspect mentality of going, the better we can keep water away from that building envelope, and however we want to do that, the more impactful we're going to have, the better performing building and structure we're going to have. So, and in every presentation, I'm sure we get the, excuse my French here, but oh my gosh syndrome, or the oh shit syndrome of, hey, let's scare everybody to death and we don't want to do this syndrome. So nobody wants water damage. Nobody wants to sacrifice to have mold or mildew or sick building syndrome in their structures. And again, that bulk water and air is just as impactful as water and in that category. So the better we can do to get water away from that structure, the better. These are the sacrifices of what will happen if we don't. Indoor air quality, damage your contents, and actually compromise the structural integrity of your building. So in the why, I think the slide has been brought up before, is 90% of the moisture intrusions or the effect of moisture gets into the 1% of the building envelope, and that's really boils down to quality workmanship, not proper detailing, having a interface of 3 or 4 different trades potentially going, oh, that's not my job, not part of my scope of work. the things that we look for is, hey, we get a pre-con meeting, we look for those potential compromises, we look for the critical interfaces and the critical details, and we can usually point out some of those compromises well before it even has the ability to have an air barrier material put on the wall, okay? Quality of workmanship and skilled labor today is one of the biggest challenges we deal with all the time. In turnover, attrition, companies getting bought, obviously, and then changing roles is part of that. The 4 different barrier types, your air barrier or water, and I'm not a big fan of the word resistive, and I'm hoping that this word resistive will go away. If it's not a water barrier and how we test to make sure it's a water barrier, there should not be a resistive to it, okay? We need to stop water in all its way and ability in any structure. So your vapor barriers and your multi-functional types of barriers. There are materials that will act as a vapor barrier, vapor retarder, and be an air barrier. So air barriers, we want to stop moisture in all of its forms, and air barriers can do that from an internal, external, how heat drive works, your stack effect, the pressure loads in your systems, equalization of your HVAC systems. And I say HVAC system, meaning is that we want to make sure our buildings are properly ventilated just as much as they're being properly heated and air conditioned. So ventilation makes a huge part and effect of how moisture can move in a structure. The water resistant barrier side of things, I'm not a big fan again of the word resistive, but bulk water is the largest damning material of actually litigation and sacrifice to that structure. So again, these are very important aspects from an air and water standpoint. Those are the largest impacts. It must be continuous, and it must be a true interface between all those different aspects of your building, meaning your foundation, to roof, to wall, to penetrations, your windows, and how they wait, excuse my expression here, but how they play well in the sandbox together from a compatibility. So it's very important that they do have the ability to work with other materials and be compatible. Your vapor barriers and how moisture moves are your largest concern. But the standpoint, it is still a potential for, and how we look at this more from a different cladding systems, but how we want to work with making sure we're controlling that moisture vapor drive. Okay, something as simple as having a capillary break in certain types of insulation to air barrier interfaces to apply the capabilities of drainage, and having a capillary break will stop vapor drive in that form. So, and then that last type of barrier system is that multifunction, can actually act as an air barrier, vapor barrier, and a water resistant barrier, water barrier in that standpoint. So those are your 4 different main types. And here's a perfect example of, well, how do we determine what's important and how they can be validated as being those 4 types. If you can see here closely and where the damage occurred here, there's actually poly back here in that wall, the inside face. Having a vapor barrier in a above grade situation of your wall in some climate zones is something that will cause catastrophic damage to your structure. So what's important is that we test these materials and have validation that they're going to be used in the right place and have a good performance on how they're being used, okay? Codes are part of that. Once it's covered up, you're not going to be able to get in there to be able to access it easily to say, hey, is this going to perform the right way? So that's why, you know, these testing validation systems of a wall system versus material are very important, and codes have a good factor to that. So here's some requirements we look at. Why are these what do the air barrier systems or these types of barrier systems, air and water, what do they need to perform to, and what are the requirements? Well, they have to have continuity, right? They've got to be continuous and have continuity. I use the analogy, I'm sure you've probably heard it before, is that when you're doing a detail or a drawing and you're drawing an air barrier system, if you pick up your pen or drafting pencil or your computer line, if you pick it up in any way, shape, or form and then put it down, you're actually losing continuity to where that actual line for air barrier needs to go. So whether you're going from below grade to wall, a wall to shelf angle or lintel, a penetration, how we create continuity detail around those areas is very important. It needs to have continuity and be continuous. It needs to be either permeable or impermeable. We can't decide that as a manufacturer. It's based off of the calculations we do in a Wolfe analysis or dew point analysis potentially of certain climate zones will be a factor of that. Amount of window space will be a factor of that. But there are specific tests that'll basically outline whether that system will need to have to be permeable or impermeable, and that's important. It needs to be durable. I mean, it's a requirement for it needs to be having high temperature stability and versus low temperature, ability or stability, strength and stiffness. So it needs to be continuous, as I mentioned, but also needs to go through really unique types of wall design systems. You can look at the picture on the bottom left there with the exterior gypsum in the yellow. From that standpoint, it'd be very challenging to use a mechanically fastened system or a peel and stick as an example to go around those different offsets, returns, or undulations on that type of wall. You're actually inviting an opportunity for incontinuity or a potential for air and water gain with the type of material you're using to actually seal up those types of interfaces or offsets. On the right, how would we detail around a potential of an interface where it comes into a structural column or a piece of steel where it has intimescent, and in dimensional stability? You see a little bit of discoloration around the black peel and stick material. Well, is that a temperature instability type of material? Or is that a primer that's being over applied that created that type of running the material? So all those things as being continuous play a factor in the materials that we use. Getting around walls, windows, doors, and roofs. Example, we want to make sure is as easy and simplistic as possible because we make it more difficult. Our contractors in the field and make it a choice on what do I use, where, and when. If you leave that decision up to them, sometimes that'll create a potential failure or problem. I shouldn't say failure, but a problem. So here's some specific tests to is a permeable E96, the types of materials testing that we see in the industry, whether the material is past certain water holdout criteria, whether it be a small material sample pieces as ASTM 2170 or a whole entire wall assembly that is as an example of 2357. Excuse me, sorry for coughing here. A little water break. I'll see if there's any questions in the queue or anybody gone, what the heck am I talking about kind of thing. So I'm just going to take a drink quick. All right, there we go.
And it has been quiet, so you must be very thorough.
Good deal. How am I doing on time? I got all right. Good deal. Looks like I can get closer to about 10 till 1, as they say.
Yep. Yeah. You've got and you have till quarter after the hour.
Awesome. Well, doing real good. I'll be sure wrapping up here in a few slides. So I've got durability. I think that's one of those just as it's I say a common sense kind of these materials need to actually be durable to basically withstand the rigors of what we see in the field. You got swing stages that are going to go across the material. You're going to have Mother Nature playing a factor, whether it be high or low temperature, the amount of moisture you're dealing with while the material is being installed. And the type of material. Say, you use example, you put an air barrier material on the wall in the morning, well, Mother Nature come in the afternoon and wash it off. Those kind of chemical resistance, okay? Is there contaminants in the types of materials that are going to be tying into the material? And as an example, UV exposure. How much time do you have these materials that are in this category to be exposed to Mother Nature from the sun and UV exposure? Will have any degradation or effect if it goes past some materials at 30 days, 60 days, 6 months, and even a year longevity of UV exposure. Strength, types of materials, your wind load versus shear load of material. Is that material going to be able to withstand those rigors of how Mother Nature will play effect on that material staying on the wall when it gets covered up, okay? The compatibility of sealants and adhesions of self-adhered flashing materials and tapes is very critical to that performance. Okay, this example is like if the material's not particularly taped, okay, it doesn't have the strength to be able to stand there without having continuity of it being taped to create one sheet. It's going to have challenges staying on the wall. So, it's not that it's a bad product. It's just that the sequence of getting that sealed up and taped in an effective time makes a huge factor. And if you're going to start with one product, stay with one product, unless it's a different wall structure or wall type. Mixing, then it eliminates any finger pointing going, hey, did you use this there? and which one, if there's any potential issues, is creating the problem. So, and stiffness goes into the same category as strength to a degree, is your ability to be able to stand loads and absorb those loads and loads transfers is very important. Code requirements, really won't get into too much of this because, you know, when this presentation came out, probably about 6 years ago, codes have been changed a little bit. It's better whether they're adapted into certain municipalities and states as well. But here's your governing body of codes, your IECC, International Energy Conservation, your International Builder Code, ABA as testing for materials, whether they're been evaluated or not, and then your ICCES. These are the governing bodies that we see in our category for categories for air barriers, water barriers, and how they're governed. So, and there could be conflicting information to what to use when. So here's a perfect example of that. Your IECC versus IBC, you got two different barrier systems and two very specific purposes, but they're two distinct codes that are what you use where and when kind of thing. So in a category of air permeability, you know, no greater, whether it be permeable or impermeable, ICC will define, hey, materials with an air permeability no greater than 0.4, and this is how everything's tested for ASTM 2178. 0.004 cubic feet per minute per feet squared under this pressure load is basically how they define an air barrier material, and that was per ASTM 2178. So it needs to comply to that to meet the requirements for IECC. It needs to be continuous. I mentioned before, you know, that's another cover for the material from a thermal standpoint. ABA defines these are the categories for being an air barrier, but there's one specific test, which is a hydrostatic head test, one test, and only one test, because ABA put in there again from an air barrier standpoint to have air barriers in our category meet that system of being evaluated. Is this robust enough? You know, hydrostatic head test. I'll beg to differ, and I can get into that much more later, but it does not really get into that true water barrier category. ASTM E331 is probably the most recognized ASTM test, but it's not enough for me, at least, and this is as a definer of going that that's why they have the word resistive and not true water barrier. So, but they're working on that. ICC and IECC and ABA are working to have a more stringent designation for having a water barrier system. And believe it or not, the building code today, the International Building Code, and this kind of falls into even sometimes a multifamily, they're still being used 15-pound felt, okay? We see it a lot of times in a multi-layer system, EIFS or stucco, we're using it as a multi-layer system, where they'll use a base material like a 15-pound felt, and they'll put like Tyvek or another mechanically fastened system over there, because the cladding system will really need a referred to as a capillary break. As I mentioned earlier, we want to stop diffusion of moisture by doing that using a very cost-effective system. This way, the two layers will stop any ability for a capillary break or diffusion, moisture diffusion by that capillary break, the two-layer system. Here's where some of the rubber meets the road. I mentioned the evaluation for materials as minimum requirements for all air barriers out there today will basically be show whether it's permanent for E96. You have a sample material test, whether it meets an air barrier, whether it be ASTM 2178 or ASTM 2357 as a wall assembly. Well, when you get into true evaluation of performance of up to 12 to 16 other tests, that's where the ICCES test for AC 212 and AC 148 criteria testing comes into play. These are much more stringent water performance testing to hold out for materials than just your standard 2178, 2357. Third-party evaluation goes along with the lab testing for AC 212 and 148, and it gets into these 12 tests essentially, okay? Much more stringent. They got ASTM E331 as part of that test, water hold out. It really gets to the point of meaning that they'll freeze, thaw, cycle, they'll do temperature range variances of these testing. And that's that's really a higher standard of test requirements when you get into specific material. So additional performance requirements is, we'll say, self-sealing of fasteners. Industry standard is ASTM 1970. You test one fastener. It used to be a nail, now it's gone to a screw, but you're basically just testing one fastener. That fastener is basically put through your material. They fill up a column of water, and if it hits the minimum mark, you passed. If it doesn't, it fails. They have moisture sensor readings there where that penetration meets the material, and that's basically a self-sealing kind of material. There are materials out there that basically will, with ASTM 330, they'll test over 50 different fasteners. So look for that in your design, going, hey, is this material, just look at one fastener as requirement? Because every cladding system out there today that goes through an air barrier or water barrier system, every cladding has got to be held onto the wall with something. And fasteners are what refer to, besides those critical interfaces of your wall, windows and doors, penetrations, and the other interfaces. Penetrations are just as damning sometimes, if not properly. You'll see fasteners that are overseated. You'll see that they're not self-sealed. They'll be bracketed with some sort of Ziegler type of system or bracketing system for your cladding. They basically will bore out, they'll miss a stud. They won't have a process for reseating that fastener and get it properly sealed. Every fastener is an opportunity for water in your system, in your building. So fastening is very important. These are your structural racking performance criteria for AC12, hydrostatic pressure on top of the AC212, AC127. As I mentioned, freeze thaw, water resistant, tensile bond. These tests are really where the rubber meets the road. AC212 also includes requirement for, depending on your structure type, whether it be type 1 and type 4, is that you're required to have NFPA 285 testing with your system, okay? And that's basically as simple as I'll put it. NFPA 281, NFPA 285 is a test that'll start on a single story structure, and it's to test the materials that go on that wall assembly that they will not allow additional combustibility or a more combustible wall system that will propagate that fire from the first floor to the second floor or floors above it faster, okay? And that's what we don't want. We want to be able to maintain and control that potential fire as much as we can on a fire rating, and not have materials that are in that wall system that are going to make it more combustible, again, to propagate that fire faster and to those upper floors. So that's as simple as basically gets NFPA 285. Again, AC 212 will come. Now, aside from that type of construction, your other types of materials that'll go into just meeting a smoke and fire index, your class A, still is in play though. So that's really a requirement below 40 feet. Third-party evaluation reports, because again, those companies that have it just allows the rubber meets the road, additional testing requirements that validates that you've gone to a point of failure, as I always put it. In summary, why use air barriers? Well, I think we covered that from the standpoint of infiltration litigation, damages, all those kind of things, indoor air quality. Okay. And review material science is important. You know, that transfer or a paradigm shift of having materials that have been a low solids or no solids to higher solids. Low solvents and no solvents are very important. We want to try to work towards getting no resistive or a resistive type of barrier out of the we'll say arena we work with. We want a true air and water barrier systems out there today, because we want to control the water in every direction. And then why AC 212 and 148 are important. So that pretty much is it. This is a summary of some things that I've done in the past on doing some spec updates. So there's some advanced training that we do in our organizations to make sure that the applicators are being trained properly to do our systems right. So I won't bore you with that. That is getting to some more proprietary information. But I think for the AIA aspect of our presentation today, folks, is concluded. And it's Friday, almost beer 30.
I guess it depends where you are. It's not even lunchtime here on my side.
Oh, I'm gonna try to see where
But I like your approach. It's 5 o'clock somewhere, right?
It's 5 o'clock somewhere. Yeah. Well, hopefully the information was insightful and had some of value. I haven't seen any questions, but I'm gonna stay here and see if there's any questions for anyone. So
We'll give it a minute or two. And I think I had cross-post the incorrect one. A couple people asked about below grade structural water barrier presentation. So you just might have to come back next month if you still have
you
that.
know what I looked at the presentation. I did the exact thing. I apologize because I was ready to do a below grade, and as a matter of fact, I've got the presentation slides up next to this because I was like, and then when I got the invite, I think from Thad to the docket of times on the schedule that said the airbrush because I presented for both. So I apologize profusely. I was ready to do below grade, and then when I saw the invite come out, I was like, okay, it must have changed. So, but I apologize. If you want, I can squeeze in 10 minutes of below grade.
A couple people asked. That would be quite the challenge. Take a 50-minute presentation in 7 minutes. So, let us circle around and maybe we can touch base and find an open slot for CSINext after the first of the year. I think there's definitely a lot of interest there, and if we can get the word out early enough and promise everyone that we're not going to do a bait and switch.
Well, I hope this isn't too much of a negative blemish on my lack of
No,
professionalism. I should have asked that. Like, hey, am I supposed to be doing airbrush or supposed to be doing below grade? So
I took the heat on it, so we're good because I figured it was something I did when I posted it and registered it. But no, hadn't seen any other questions, so just kind of to follow up with everyone. When we end this webinar, you should get a web page popped up, and it'll say, stay on Zoom or switch to CSINext. If you do accept that CSINext, you'll get the webinar form to be able to make the request for the certificate, and if you need an AI credit to plug in your number there, and then we will get that information to Garrett and hopefully get it posted within the week and help everyone with their end of year. I was just looking at my credits, and I am exactly 4 shy for the year, so this has turned out to be quite the nice day for me.
God. Well, I don't want to put a plug. It's not my intent, but if there's any questions you may have, you want to write down my email. I will be. My role for 25 is expanded to where, with all these acquisitions and mergers, it's been a challenge for us to keep up with a lot of the naming through the different organizations over the years. And so if there's anything I can do from a help of steering the direction, hey, this name has changed to that. I've been updates. Let me know. That's been a big line share of my role for coming up in the next several months to just get everybody consistent and update with some of the namings. So.
Absolutely. Yeah, everyone take a moment to capture that contact information for Garrett. It's always nice to have someone like you to reach out to. This is always one of those tricky, sticky topics.
That is. Thanks everyone for the opportunity to share some of the information. And if there's anything I can do to help, don't hesitate to call, text, email, or anything like that. Hope everyone has a great weekend.
Thanks, Garrett. Appreciate it. And same for everyone else. And we'll see you in about a half hour for those that have signed up for part 3.
Thanks, everyone.